Start our today seminar, and we happy to have Emanuel Diaconescu from Rutgers, who will speak about flops and Hilbert schemes of space curve singularities, and slides are in the chat. Please.
Okay, thank you, Ian. Thank you for the invitation to speak here. What I'm going to talk about today is recent work with Mauro Porta, Francesco Sala, and Arian Vosoughinia, who, by the way, was just an undergraduate student when he started working on this project initially. And it's very much related to a paper that Jan and I wrote together with Zheng Hua more than 10 years ago. And I think the connection will become clear, at least for Jan. So what is this about? So first of all, the main idea is to use birational transformations in enumerative geometry to learn something about the topology of punctual Hilbert scheme of space curve singularities. Because after a long search through the literature, what I realized is that almost nothing is known about the topology and the geometry, if you want, of the punctual Hilbert scheme of space curve singularities. And we're going to use an approach based on birational geometry for complex threefolds. So just to set things in the right context, the motivation for this, as I said, goes back to more than 10 years ago. Yeah, so the motivation goes back to more than 10 years ago. It starts with this conjecture of Oblomkov and Shende, which they conjectured a very precise connection between the topology of Hilbert scheme of plane curve singularities and Humphrey polynomials of the associated links, which means you have a singular curve in C2, if you want, in two-dimensional complex linear space, with let's say a unique singular point, and you surround that singular point with a small sphere, Euclidean sphere, in a three sphere. So the intersection with the curve would define a link or a knot. Well, and the Humphrey polynomial of that particular link is related in a very precise way to the Euler numbers of the punctual Hilbert scheme of the curve. And then what happened is that after this conjecture came out, there were two papers. One of them, as I said, with Jan and Zheng, and the other one, a paper with Shende and Vafa, which tries to explain physically what happens when it plays this conjecture. What we learned this way is that this conjecture is actually a manifestation of Lagrangian duality. And the Hilbert schemes that occur in this context are, in fact, a special incarnation of stable pairs on a resolved conifold. And the connection to knot invariants is explained by Lagrangian duality. So this is what happened back then. And then a few years after that, Davesh Maulik, using this three-dimensional setup, complex threefold setup, gave a spectacular proof to the Oblomkov-Shende conjecture using conifold flop transitions. So these are birational transformations among Calabi-Yau threefolds, which basically contract -1, curves. So as you say, I mean, this is stuff done quite a few years ago. What my recent interest in this topic is basically motivated by trying to understand what can we learn or what can we say about space curve singularities. I mean, space curve singularities, as you can easily imagine, are very hard to classify, first of all, because for a plane curve singularities, you have one polynomial equation in C2. For a space curve singularity in three-dimensional linear complex space, you can have any number of polynomial equations, right? Because it's not necessarily two. And the defining ideal can be generated by any number of equations, and you get a the landscape of possible examples or models is huge compared to plane curves. So that probably explains why no systematic approach was attempted, or there is no systematic approach anyway in the literature. There is a result obtained, a result proving that the by Bergeri, Ranganathan, and Vakil, proving that the a rationality result for the motivic zeta function of Hilbert schemes of reduced irreducible singular curves. So this is a strong result, but at the same time, it doesn't offer explicit expressions for the zeta functions or even for the Euler numbers. So what we want to do is to study this problem using what's called the pagoda flop transition. This is a more general type of flop transition than the conifold. So in the process of doing that, we will simultaneously generalize the work with my work with Jan and Zhang back then in 2012, and also Maulik's setup to a more general class of birational transformations. And this was inspired by a similar approach used by Toda to study the topology of punctual Hilbert schemes of singular surfaces. So he used this approach. You have a singular surface in a smooth threefold. You study the behavior under birational transformations, and he managed to derive explicit formulas for generating functions of Euler numbers. So so all this converges towards this idea that we want to try to study space curve singularities, the Hilbert scheme of space curve singularities, using such birational transformations.
Emanuel, but the relation at the level of enumerative invariants, it's sort of a wall crossing.
Yeah, we'll get there. That's those are my last 3 slides on the.
All right. Okay.
Those are my last 3 slides on the.
Okay.
Yeah, the details are a bit involved because, well, you'll see that you have to say many things if you want to paint a clear picture. So first of all, the basic picture these are transitions discovered by Miles Reed back in the 80s. You have 2 smooth projective threefolds. Everything is over complex numbers, which equipped with 2 contraction maps down to the same singular threefold X with a unique singular point, satisfying some natural conditions, reduced, irreducible, normal, and so on. The important thing is that F plus and F minus contract 0, -2 curves. So the exceptional loci of these contraction maps are rational curves, like projective lines embedded in Y plus and Y minus, but they're embedded in such a way that the normal bundles are of type 0, -2, as opposed to -1, -1, and they have a finite width. So if you think about the local geometry or the geometry of the infinitesimal neighborhood of the curve of such a curve in the ambient threefold, it's a lot more complicated than just the conifold geometry, because the infinitesimal neighborhood is not determined by the normal bundle in this case. So this is the setup. You can actually, I should have probably done that to make it more concrete. You can write up to complex analytic isomorphisms. You can write a local equation for the singular point here. I didn't do it because I don't use it, but just for completion, just completeness, the equation you get here in local coordinates up to complex analytic isomorphisms, it's x squared plus y squared plus z squared plus w to the 2n equals 0, as opposed to the conifold equation, as opposed to the ordinary double point. All right, so now what I need to, if you want to assume about this geometry, I have to make a couple of assumptions in order for me to be able to get to realize my goal. And this is a technical assumption. So what it is that basically it says that there is the geometry provides for you a preferred, if you want, chain of nested thickenings of my 0, -2 curve of length n. Okay, so you have a couple of non-reduced curves inside the threefold, which are all thickenings of the same projective line sigma, and they sit inside each other. They are nested like this, and the structure sheaves fit in this exact sequences like as this on the bottom line of the slide. Now, this is just to give an idea what's happening. And
can you a little bit comment on these strange
yes.
conditions? Yeah.
Yeah. Okay. So yeah, I should have said more about this. Yeah. So okay. So Miles redefined the width of a 0-2 curve, a contractible 0-2 curve, to be the maximum length of such a chain. Okay. So the maximum possible length of such a chain, and there is a way of converting that into this definition into a filtration of the defining ideal of sigma. Now, this conversion, this equivalence between one and the other is claimed for complex analytic spaces, and even there, I don't completely understand the proof. So I just can't tell you that. It's okay. So I don't completely understand the proof, but more than that, I couldn't see how to transplant this proof from complex analytic spaces to projective schemes. So the bottom line of all this is that instead of thinking, the geometric intuition will require me to think about these nested thickenings because that's something concrete geometric. It's much better to think about, to define, if you want, this the width and through a filtration on the defining ideal. So there is a filtration of length n of the defining ideal satisfying certain conditions, which I'm not going to try to explain for now. These are the conditions you write down. They are fairly technical, but they tell you, the claim is for complex analytic spaces, they tell you that somehow you can only construct a unique chain like this and it stops at n. You can no longer add, you can no longer extend by and yet another thickening sigma n plus 1 satisfying the same conditions.
So for the resolved conifold, it's n equal 1.
Yeah, the resolved conifold is n equals 1. So they have almost nothing. It's just yeah. It's n equals 1. Yeah. Okay, so maybe this was maybe too technical, but this is the kind of definition I'm gonna employ. If you want, this is my working definition for a width and 0-2 curve, and this is the one I used. And in practice, if you write down these threefolds as hypersurface and toric varieties, for example, which we did, you can check these conditions. I mean, this is, you have local coordinates, you go in and do your computations, and you can check the conditions, no problem. But an abstract proof, I just, we couldn't give an abstract proof. And well, we are also none of the authors is really an expert in birational geometry, so maybe that should be a disclaimer. Okay, so now that's the setup. Now this is the more important part of the, so if you're on the second part of the setup, the geometric setup. So we start out with a smooth veiled divisor in X, in the singular threefold X, which passes through the singular point and contains a plane, a reduced irreducible plane curve. So W is a smooth surface passing through the singular point. Think of X as the singular hypersurface. W is just an affine space of dimension 2, if you want, locally. And the curve is some singular plane curve, which is singular exactly at the singular point of C coincides with the singular point of X. Okay, and then you look at the strict transforms and what happens under this contraction by pullback. If you take the inverse image under these two contraction maps, and because of the flop transition, something interesting happens. Let's say on the plus side, we can, well, by choice, by how I chose my notation, on the plus side, nothing happens. So the strict transform of W in here is just a copy of W. So the S plus is isomorphic to W, and there is the strict transform of C in Y plus, again, is isomorphic to C. So this picture, C inside W, is transplanted by taking inverse images into C plus inside S plus. Nothing happens. I have a plane curve right there. And on top of that, S plus intersects my my 0-2 curve transversely. So I'll draw a picture in a second. Now on the other side, something interesting happens because the strict transform of W, because the way you do the contraction now turns out to be a singular surface. Okay, so it's no longer smooth. It's a singular surface. It's a unique singular point of type AN. And C minus now becomes C becomes by straight transform becomes a curve C minus, a singular curve inside the singular surface, which again is singular at the same point as the singular surface.
So, Emanuel, I'm confused with the notation. Your sigma before you identify y plus and y
no,
minus.
no, you're right. I'm missing a plus. I'm sorry. Plus, okay. I'm missing a plus on sigma. I'm sorry.
Okay.
That's just a typo. Yeah. But let me just draw the pictures. It's much nicer to look at the pictures. So if you want, this is a cheat sheet. So I have these are sigma plus and sigma minus. S plus here, it's a smooth surface inside the ambient threefold, and C plus it's a singular curve inside S plus, and everything intersects sigma plus transversely. This is the picture that Jan would remember. This is the picture we had for the conifold, but now it's not the conifold because it's this more complicated threefold. On the minus side, what's happening is that the S minus is a singular surface. The singularity is right here in this corner, in this bottom right corner. It contains sigma minus as a curve inside. And also the strict transform of C minus, the strict transform of my plane curve, it's a singular curve inside the singular surface. So it becomes a space curve, a singular space curve, because it cannot be written as a single polynomial equation in a smooth surface.
It's the same n, it has...
Yeah, same n, same n.
Okay. Same
n, because this singularity occurs as a result of this flop. Yes, it's exactly the same n. Yeah. Okay, so this is what you have to keep in mind. This is like the if you want the cheat sheet for this geometry. So the plan is then to try to use this birational transformation to relate let's start here, to relate the Euler numbers of the punctual Hilbert schemes of C minus with support at P minus in terms of something that you compute in terms of C plus. And that something will reveal itself. It's some sort of a flag Hilbert scheme for C plus, but it's not one of the conventional flag Hilbert schemes that appear usually in the literature. It's some kind of refinement, and I'm going to explain what kind of refinement. So yeah, so what is the counting function associated to C minus? First, this is easier, somewhat easier. So we have a moduli space of stable pairs. So I have section, F is the rank 1 torsion-free sheaf on C minus. S is a non-zero section whose co-kernel is supported at P minus, set theoretically, and it has length K. Okay, since S is a non-zero section, the co-kernel is necessarily a zero-dimensional sheaf on C minus. And I just make a generating function by using just the Euler numbers of these moduli space of pairs. Now that's the easiest thing to say. And then now using results of Panda and Thomas, if C minus is LCI, which means local complete intersection at P minus, roughly speaking, if it's defined by two independent equations, right? And only two, then you can, using their results, you can prove that this moduli space of pairs, a stable pairs, is actually isomorphic to the punctual Hilbert scheme of C minus, but only in that case. And the reason for that is because this LCI condition in codimension 2 implies that C minus co-Reinstein. So it has a locally free dualizing sheaf, or in other words, a dualizing line bundle. And using the dualizing line bundle, this, and results in Panda-Dependent Thomas, we can prove this isomorphism. I mean, they did it actually. They did it for plane curves, but the proof is exactly the same once you know that the dualizing sheaf is locally free. And it's a sheaf, not as opposed to a complex. Okay, so this is what we're doing on the minus side. Now, C plus, that's going to require a bit more detail. There is a counting function for some kind of flag Hilbert scheme, but the flag Hilbert scheme is defined by a rather, well, exotic condition, something that hasn't been studied or that hasn't appeared in the literature so far. So what happens, look at the geometry of S plus. So we have, this is S plus, the smooth divisor inside UI plus. C plus is the smooth curve, the singular curve. And then remember, sigma plus sticks out of S plus. It intersects transversely. Now, but at the same time, sigma plus has a if you want, a canonical thickening, which is provided by the geometry of the threefold. So the canonical thickening is sigma n plus. And you take, now we take the scheme theoretic intersection between sigma plus and S plus. So we get this blob here, this green blob is meant to represent some kind of scheme theoretic thickening of P plus inside S plus. Okay, so you just have a scheme theoretic thickening of this guy in there. And now you look at the flag Hilbert scheme, which is as in nested ideals of zero-dimensional subschemes of C plus, such that zero-dimensional subschemes which are set theoretically supported at P plus. But what's the important condition is that this quotient here has to be scheme theoretically supported on inside Tn. So this is a condition that's kind of bizarre if you think of it from the in isolation without looking at the whole geometry. If you think of it in isolation, for this plane curve, it's a bizarre looking condition, but that's what you want to impose, this condition right here. So it's a scheme theoretic condition on the quotient, which is actually, it plays a very important role in this in our setup. So this is the kind of a flag Hilbert scheme, and then you make a generating function again by taking Euler numbers.
Just a second, let me ask. The class here is just the Euler characteristic, or you talk
Yeah.
about
So I forgot.
length.
I'm writing topological because I want to emphasize that this is not a virtual Euler number. It's not defined through like Behrens constructible function, or it's just plain Euler number. It's a topological.
Even in the previous slide that
all chi's in this talk will be topological, all of them.
Yeah, I see.
I'm not gonna use.
It's not about the length of the sheaf. So, for example, that chi O C minus quotient with I.
No. This is not the holomorphic Euler characteristic of a sheaf. This is just the topological Euler. See, this is a topological vector space. Well, it's a singular scheme. It's a scheme. It has
It's supported at one single point, so it has finite length. So I was thinking of the case, the length, or
it's not the length of a sheaf. This is the topological Euler characteristic of the underlying topological space of the scheme, modularized scheme space.
Okay, thank you.
Yeah. It has nothing to do. But the question is, I forgot to emphasize that we are not using virtual Euler characteristics here. We're not using any non-trivial, like the Behrens constructible function or anything else like that in the talk. This is like the most basic version of what you can do. And then this is the main theorem, if you want. The relation, these two generating functions are related, in fact, by a simple, by rescaling by some power of Q. I forgot. L is just the length of this quotient. So L is the length of I didn't write it. Yeah, I wrote it. Okay, and this number L is determined. It's determined by how the curve, the homology class of the curve C plus, is related to the homology class of C minus through, or I should say that there is a natural isomorphism, if you want, phi Lowenstock between the homology of Y plus and the homology of Y minus. And this is telling us how this isomorphism acts on the homology class of the two curves. I mean, how it relates to the homology classes of the two curves. They differ by a multiple of the exceptional curve here. And now this is the main result of this work, which is that the two for transition function, generating functions are related through this identity. And that determines, in principle, it allows you. Yes.
The phi Lord star that defines the map between what for Y plus and Y minus in the true rings or cohomology rings.
Yeah. Okay. I was. Yeah. The correct thing to say, it defines a map of numerical equivalence classes of 1 cycles.
Okay, thank you.
Yeah, that's the statement. Yes. Yeah, so it's telling you how these two classes are related, and they differ, not surprisingly, because they are both the strict transforms of the same curve in the singular threefold. They differ by a multiple of the exception curve. All right, and now this is one form. This is the main result. This is how it's telling you how they're related. But now you can say, well, fine, you prove this relation, and actually it requires a lot of work, as you'll see. And I'm going to try to explain the main steps in the proof. But then you say, well, can you compute at least one side? Is this good for anything? Does this yield any explicit results? And the answer is that yes, we can actually derive explicit results using this theorem. If, at least for a series of examples, not for anything, not for any possible curve. I mean, this is clearly this was expected, because space curves can be pretty wild. But if you choose your singular curve C to be this very simple curve, this is one of the plane curves that was studied very intensively in the last 10 years. X to the arc minus y to the s equals 0 for two co-prime integers, R and S. And furthermore, if you choose S to be a multiple of n, where n is this n provided by the transition, then you can work out what C minus is, and you can learn that it's an LCI curve. This is, to my knowledge, this is like the simplest series of examples where we can actually prove that the strict transform, it's an LCI curve, which is defined by two polynomial equations locally. And it's easy to write down all sorts of other examples where you can't even write down, you can't even find an explicit set of generators for the defining ideal as C minus. It's difficult. This is a difficult question in birational geometry, but for these examples, it works out nicely. And it also works out in the sense that using the theorem, we can provide an explicit formula for Z minus, which is written here. This is just I'm not going to explain the detail, but the abstract is just a rational function of Q. This construction here just produces for you a rational function of Q, which is obtained by actually computing the plus side. Okay, so this right-hand side of this formula comes from the plus side.
Is it always rational?
Yeah, I'll get there. I'm going to answer your question, I think, on the next slide or in 2 slides. It's a very, very good question. Yeah, there is something you have to say about this. I mean, these curves, and not surprisingly, both curves are preserved by some torus action. So in principle, you could try to compute the Euler numbers by counting, by the fixed point theorems. The problem is, if you try such a brute force approach for C minus, you end up with a very complicated combinatorial problem to classify the fixed points here. And it's basically untractable. So this theorem, if you want, from a combinatorial point of view, in this particular case, it makes that problem tractable by moving to the plus side. And on the plus side, you can actually do you can sum the series like this, explicitly. Good. So now here's the Jan's question. There are standard, if you want, some of the standard conjectures in numerator geometry predict that formulated first by Condorcet Thomas, and then there is a variant formulated by Toda for topological numbers, which is exactly what we're using today. Predict that Z minus has to have this form, has to be an integer polynomial with integer coefficients divided by y minus q. So this is a very strong statement. I mean, it's not by any means obvious when you formulate the problem. It's a strong and well, there is some further statements about the speed that can be conjectured, but I'm not going to get into that. But interesting, I mean, what's interesting about this, about the formulas that I just wrote on the previous slide, is that you can actually verify this conjecture in many examples. So you can, if you want, what you can do, you can plug into Mathematica or Maple and evaluate this, and every time you evaluate and you simplify it, you get exactly the kind of formula that predicted by the strong rationality conjecture. at the same time, I don't quite know how to prove. There is something, a combinatorial exercise to be done here, which is to take this explicit rational function defined here and prove that it has that form. So this has nothing to do with geometry. It's just something to do with combinatorics, I mean, calculations, rational functions, and so on. This is some fun exercise that I haven't really tried very hard to solve, but it's kind of a good exercise for another graduate student, I guess. Okay, so now these are the main results of this work, and then what I'm going to do in the remaining half an hour is to go over the proof, because for me the proof itself it's an interesting journey, in my opinion. So this is something that a result like this for the conifold. So the major question is first of all, we're going to be working on the plus side for quite a while. So I'm going to drop this plus label because it's upper script, because it keeps getting in the way. To simplify the formulas, I'm going to just drop it, keeping in mind that we are on the plus side until I say otherwise. So the major question is how to convert the flat Hilbert scheme of C+ into something geometric on the threefold. What kind of geometric objects on the threefold do we get? And this is something that was done in the paper, my paper, and the paper with Jan and Zhang, through some construction of using stable perverse coherent sheaves. Here we're going to follow a different approach, because since that paper there were a few other developments in the meantime. So we're going to use this important notion of F stable pair developed by Brian and Steinberg, and this is a construction they carried out with the goal of proving the Crepin resolution conjecture for Donaldson-Thomas or Kandari-Pandya-Thomas invariants. That was the motivation for them to design this, to come up with this notion. Here we're going to use it for our own purposes. So what they did was you start out, you define a torsion pair on the abelian category of coherent sheaves on Y, where the torsion part consists of all sheaves on Y, such that the right push forward to the singular threefold X is a zero-dimensional sheaf in degree 0 and nothing else. So all higher direct images vanish, and the zero direct image is just a zero-dimensional sheaf. So it's a sheaf supported at some points in X. That's it. That's the torsion part, and the torsion-free part is just the orthogonal inside cohort of Y. And then in this setup, the notion of stable pair defined by Brian and Steinberg is that a stable pair is just an F stable pair. It's just consists of a pure dimension 1 sheaf F, which is on Y, which is torsion-free, which lies it belongs to the torsion-free part of this torsion pair, and a section such that the co-kernel belongs to the torsion part. Okay, so this is the notion that they use. And the first result we had to prove in this context is that there exists, it's a constructive result, there exists the right algebraic moduli space of such objects, which is also a finite type for fixed topological invariants. So yeah, so this is something that this was the foundational result, first foundational result we had to prove in order to substantiate all the following steps. Now, in our setup, we are going to impose a frame, what's so-called C-frame condition on this object by requiring the sheaf F to fit in an extension of this form. Namely, F decomposes in the sense of an exact sequence like shown here into a rank 1 torsion-free sheaf on C, extended by any kind of pure dimension 1 sheaf with support on sigma. Okay, so we ask F to fit in such an extension. That's the notion of framing for my F stable pairs. That's where C comes in. Initially, in their work, of course, there is no fixed curve. C comes in this way. Okay, and then we construct, basically we construct a moduli space of C frame F stable pairs, basically by base change, by pullback. So we have a moduli stack of all possible extensions, which maps to coherent sinks on Y by the central projection. So mapping such an extension to F. So moduli stack of exact sequences, and then you define the framed moduli space, the moduli space of framed C-framed objects through this Cartesian diagram. This is the best way to think about this moduli space. So this also proved that it's a derived algebraic space, locally finite type. And then the question is, how do we get, as I said, the question is, how do we get from from this flag Hilbert scheme of C plus, now plus has disappeared from my notation, but it's the flag Hilbert scheme of C to C framed stable pairs, F stable pairs on Y. And this is something that's, it's in the end, the claim is that they are in fact isomorphic. You can construct an isomorphism, but the construction is not very direct. The construction goes through a third moduli space, which is a relative Hilbert scheme, which is a relative quad scheme of some kind that I'm going to explain in a second. So yeah, so this is the moduli space of C-frame F stable pairs. I think I'm missing a K here. I should have a K. K is just a numerical invariant that disappeared, but yes, it should be there. L tells me it's just determined by the second Chern character of F sigma, of the component of F that's along the exceptional curve. So then you have, we are constructing a relative quad scheme over so the third actor in this game, it's a relative quad scheme over a moduli space of stable pairs on C. So these are usual stable pairs, sections of rank 1 torsion-free sheaves with co-cardinal supported at P, set theoretically, and some fixed length. And so this is the kind of pair objects used by Pandare-Pandey and Thomas. And now we're defining a relative quad scheme to be which is defined through as which parameterizes quotients of F over this I should say better said is quotients of the universal F over the this moduli stack of pairs, moduli space of pairs, subject to certain conditions. So namely, they are of course supported at P. This projection map composes applied to the section S is 0, and then it has a scheme theoretic condition. Again, the quotient is scheme theoretically supported on this fixed 0-dimensional subschemes Tn. And then we can use results of Pandare-Pandey and Thomas. Since C is a plane curve, so in particular it's Gorenstein. It has a locally free dualizing sheaf. We can use results of Pandare-Pandey and Thomas to prove that the flag Hilbert scheme is equivalent to this quad scheme. So somehow this is the first step. We are converting this flag Hilbert scheme into something that has something to do with stable pairs. But these are just stable pairs on the curve. And then the second step would be to try to extend to make a connection to this F stable pairs on the threefold. And this is something similar to the analysis done in this paper with Yan and Zheng, except that the technology has somewhat improved since then. So the idea is to look at F stable pairs, C-framed F stable pairs, so some which are defined by diagrams like this. So you have an F that fits an extension and the section of F. And you want to try to understand, to prove certain structure results for these objects, for these diagrams, following from stability, this notion of stability condition. And the very important thing is that you can prove that F sigma is a semi-stable sheaf of slope minus a fixed slope And then there is going to be some non-degeneracy condition on the extension. And then using this results of this nature, you can prove that this chord scheme is then isomorphic to the moduli space, that moduli space of C-framed F stable pairs on the threefold. So it's a rather convoluted, complicated procedure construction, but this is what allows me to convert an object that a priori is defined in terms of C plus into C plus or maybe S plus, and this zero subscheme T and into objects on the stable pairs on the threefold. So this is the most technical part of the proof, how to go from one to the other. And then the proof involves two more steps. There are two more steps involved. The second step is to prove a wall crossing result. This is analogous. It's analogous to a result proven in Bryan and Steinberg. In fact, it's a C-framed variant of a wall crossing formula, which relates C-framed F stable pairs to just C-framed stable pairs. So I'm dropping the F, and I'm just going to convert these things. I'm going to relate them further by wall crossing to C-framed stable pairs. So by stable pair, these are stable pairs defined by Pandare and Thomas. They are defined by diagrams like this, where the co-cardinal of S is zero dimensional. And again, I'm going to require F to fit in an extension of this form. So I'm just dropping the F from that from the left-hand side. Now the relation between these objects is not very immediate or obvious. It requires a rather involved wall crossing analysis to relate them. Or you better say what you relate is the motivic classes in the motivic whole algebra, motivic whole algebra classes, not directly the moduli stacks. But what you prove when the dust settles is that, well, these are our counting functions. So you have a counting function of Euler numbers for F stable C-frame pairs and for C-frame pairs without F, just stable pairs with no F in there. And you can easily prove, I mean, not easily, but you can just following the steps of Bryan and Steinberg, we can prove this identity. This is a wall crossing identity which goes from one to the other. So now I drop the F. Everything is written in terms of stable pairs on the threefold subject to certain conditions, framing conditions along C. The denominator here, this X, stands for stable pairs with support on the exceptional curve. So this is a formula. Such a formula was also initially proven by in our paper from 10 years ago or 11 years ago, using a different construction, using variation of stability conditions for perverse coherent sheaves, following Toda's work. But we still prove the factorization like this. Actually, here we're doing it in a somewhat different way. There is no need to actually study a variation of stability conditions, somewhat a more direct analysis, but it's really an adaptation of a similar formula proven by Bryan and Steinberg without framing conditions. And finally, the third step, it's just the fluff formula itself. This is something well established by now. You have to use these are use results proven by Toda and Calabresi, who basically relate the stable pair, counting functions of stable pairs on Y plus to counting functions of stable pairs on Y minus, or if you want Donaldson Thomas invariants of Y plus and Y minus in a very precise way. And again, you need to prove a C-framed formula, a C-framed variant of their results. And this is also proven by wall crossing. It's proven by wall crossing, and this technique for C-frame variant, this is really a straightforward generalization of Maulick's results. So this is exactly what Davesh Maulick used for conifold transitions in his proof of the Oblomkov shedding conjecture. Here, we're just using a similar result, except for this more complicated pagoda flop transitions. The end result is the same. The way you relate the counting functions in the end, formally the identity looks formally the same. So this is what allows me to convert F-stable pairs here to F-stable pairs there. And then finally, if you go back to Hilbert schemes and you unravel all this all these results, you can obtain a proof of you can obtain this identity that I stated in the first part of the talk, which is this identity between generating functions associated with Hilbert schemes of curves. So when the dust settles after this long journey, you go back and then everything is packed in terms of Hilbert scheme of curve singularities, provides some way of relating space curve singularities to plane curve singularities, but the relation, as you see, it's not extremely. It involves this rather complicated flag Hilbert scheme on the plus side, which hasn't been studied much in the literature. Okay, so we have, I still have a few minutes left. I can conclude maybe with some possible open questions or open directions. Since my approach is, approach this problem issue as a physicist, a natural connection is, can we in this context find any connection to not invariants through large N duality? And this is a question that has been a very frustrating issue for a long time, because it looks like large N duality is trying to give us hints to a possible connection, possible answer, but I just haven't been able to decipher the message. So as it stands right now, I don't know how to use large N duality to derive such a relation, although there are some hints, some indications that something is going on. Just I don't know. I can't really figure out what. We can't really decide. It's a bit like talking to an oracle.
But for this old paper which you mentioned and the Blomkov, Schende, blah blah blah, so they suggested some formula for Homfle and using this very specific geometry of the resolved conifold. So you are looking for an analog of that result, how to.
Yeah. So basically, you can try to play the same game. In other words, you take these hypersurface singularities, which is, as I said, I should have written them: x squared plus y squared plus z squared plus w to the 2n equals 0.
Yeah.
And you deform it. You don't blow it up. You don't resolve it. You don't just deformation. Add instead of equals 0, it's going to be equals epsilon. So that's a deformation. That's exactly how large N duality works for the conifold. And then you have to study somehow some kind of Chern-Simons theory supported on the vanishing cycles. But in this particular context, I'm getting a strange picture that I don't know what to make of it. I'm getting something very strange, like Chern-Simons theory, Chern-Simons theory of a singular threefold. I mean, real threefold, like two spheres intersecting somehow. It's a very strange picture that I can't decipher. But it gives you, it's like it's trying to tell you something, but we just can't. We don't know what it is.
If you complexify, so you cannot speak about connections on the singular threefold. But
so I don't know how to approach that problem. It's a strange picture. The threefold is really two spheres that intersect transversely. And well, sorry, it's not transversely because you're in a 6 manifold. So but anyway, they intersect along a two sphere. So and then I just can't make sense of not invariants in such a. I mean, I don't even know what. There is something off about. I mean, okay. It's I just want to, it's an open question that
Yeah, it's interesting. Yeah.
It's very interesting because this was, in some sense, this was the goal, the initial goal of such a project, but the picture turned out to be too not explicit, not clearly, not very clear. And then, of course, you need to. Another question is if there is any connection to the representation theory of Cherenkov algebras or double affine Hecke algebras. Again, not very clear how to approach this. The only connection to the representation theory I see in this context is actually as in Yan papers. I have reasons to believe that using the cohomological Hall algebra of zero sheaves in C3 acts on the Borel-Moore homology of or some kind of vanishing cycle homology of the Hilbert scheme.
I remember we discussed that with you long ago when I wrote that paper, and you made some computations which were a bit disappointing. That
no, but back then my knowledge of cohomological algebras back then was too sparse. No,
yeah,
I think it's possible to. I mean, you just have a singular curve in C3. And the Hilbert scheme of the Hilbert scheme of that curve is a close subscheme of the Hilbert scheme of C3, right? And in your recent papers, Jan, you constructed an action on.
I see.
Yeah, so then you just pull it back by using the correct version of pullback for these shifts of vanishing cycles, and then try to check that the action and so on, and then you have to check that you can double the action and you can construct it like something like a Yangian algebra acting on this, things like this.
Depending on the cohomology theory.
Yeah, depending on So this is the kind of thing that I envision right now. I mean, connections to not invariants. This is a lot more obscure. These connections to not invariants, but
it's interesting. Maybe we should kind of
an action of the vanishing cycle, Koha vanishing cycles, and for zero sheaves in C3, and that I can envision. I mean, there could be some technical difficulties, I don't know, but that I can envision. I don't know. So maybe in some indirect way, we'll also learn something about Dahas, right? Because if there is some Yangian appears, and the Yangian is a limit, it's constructed by this limiting, like in Shimon and Vasserot. It's a limit of Dahas, essentially, or spherical Dahas, or whatever their construction is, then perhaps we could learn something indirectly about an action of some kind of action of a double affine Hecke algebra in this context. Possibly, I don't know. But the connection to not invariants seems to be mysterious at this point.
By the way, I vaguely remember there was a paper by Cherenkov himself about torus knots, and maybe I'm mistaken, but he considers some flags of ideals, but probably consider only planar singularities.
Yeah, for planar curves. Yeah, so this is also connected to this. Maybe I should say a bit more about this conjecture. This conjecture that it's right here. Here, this is this strong rationality conjecture. This P, I mean, if you did this calculation for virtual Euler characteristics, right? This P is expected to be related to some kind of perverse, if you want, E polynomial of the compactified Jacobian of the curve. So there is some story that you can tell. Normally that story comes from this construction of Kopa-Kumar-Vafa invariants using sheaves of vanishing cycles, carried out by Maulik and Toda. So in any way, this P is somehow related to the homology of the Jacobian, of the compactified Jacobian of the singular curve in some way. Related to a certain filtration of the cohomology, in the plane curve case, it turns out that the kind of filtration you get, it's a natural filtration because it's you just you take a generic one parameter family deformations, and that provides a perverse filtration on the homology of the Jacobian and at the center. For space curves, again, this is a more mysterious question. We don't know exactly what's the correct filtration, or if there is an explicit construction of a filtration on the homology of the Jacobian that would give us this polynomial P of Q. In the examples we computed, it's interesting because this polynomial has some symmetry properties that are reminiscent of some kind of Poincare duality, but it's just these are just experimental observations, but it's not clear how to. First of all, it's not clear that how this is related somehow to the homology of the compactified Jacobian via some filtration. So that's another question that perhaps should go to the list of open questions.
And no integrable systems nearby because your curves, they cannot be thought of as kind of spectral curves because they are space curves.
Yeah, usually spectral curves occur. Yeah, they are plane curves. These guys are. Yeah, we've been working on this for a while. The thing I learned is that the space curves tend to be a lot wilder. I mean, you don't. I don't know. Don't know exactly. Yeah, I don't see an integrable connection here. But I don't know. It could be that there is something I'm missing. I don't know.
Yeah. By the way, about this rationality, I mean, this is really very strong conjecture because it even predicts what is a set of singularities. It's just one point. But since this wall crossing story was involved, we, like some time ago, we introduced with Maxim the notion of, I mean, we sort of studied wall crossing structures and we divided them into different classes. Like, for example, algebraic wall crossing structures, they in the end produce generating functions, or they are related to generating functions which are algebraic in the end. And we explained in this way some results, I believe, of Clay Cordova, and maybe more, I don't remember. But we also introduced a class of rational wall crossing structures, and this means that these certain elementary transformations, they are sort of matrices with entries which are rational functions. And there are examples, but they seem to be very far from this geometry. For example, if you want to count saddle connections on a Riemann surface, it's Gayoto-Murnitsky old stuff. Then the corresponding wall crossing structures are rational. And so in the end, it implies some rationality restrictions on the generating functions of this number of saddle connections. So then I'm not sure, but maybe there is some rationality. The reason, since you mentioned that besides of geometry, you need to prove something about rational functions, like to do something which is not.
No, that was just if you want to, let's say, prove this conjecture for this series of examples we have here, all you have to do, it's an exercise that looks elementary. I don't know, I haven't tried it. I haven't tried to solve it, to do this. Take this is a rational function. It's fairly complicated, but it is a rational function. Try to prove that it takes this form. This is a very, low, very simple-minded approach. It's just an exercise that you can even, you give to an undergrad student. I don't know if it could be an exercise that it's hiding something a lot more sophisticated behind. It's just a, the tip of the iceberg for something much more sophisticated, or it could be just an exercise in irrational function computations. I'm not sure. But if this is done to prove that this takes always this form, at least it would be a proof of this conjecture for this series of examples. As it stands, we just verified by explicit computation, we verified indeed that we get the results of this form. And these P's are quite interesting. I mean, these P's are, as I said, they have a symmetry property that is reminiscent of some Poincare duality somewhere. And I spent a long time trying to relate them to all sorts of not possible, not invariance combinations, all sorts of, nothing worked in the end. I couldn't make it work that way. So that's the, but I think they are very interesting invariants. So there could be something interesting to, yeah.
Maybe computations or finite field.
That's another good question, right? So if you do the curve plane case, there is a interpretation of all these formulas in terms of counting rational points on character varieties.
Yeah.
So yeah, because you formulate the problem in terms of Higgs bundles on the curve, and then, as you said, by thinking about this singular curve as a spectral curve, and then you have a non-abelian Hodge correspondence, which takes you to a character variety, and you can count rational points. But here, I don't know how to formulate any kind of rational point counting problem that gives me these polynomials, because yes, I can. There is some kind of, I can think of the curve as some kind of spectral data if you want on the affine line, but it's kind of, you get Higgs bundles with 2 Higgs fields instead of 1, because they come from curves in 3-dimensional space. So I have, if you want, in the local case, you have a Higgs bundle on the affine line with 2 twisted endomorphisms instead of 1. And once I have this picture, I can't see how to convert this into anything like a character variety or connections of some kind, or, you know, and I don't know how to formulate to guess or conjecture some kind of rational point counting problem that's somehow related to this. There is no, I don't have a lead into that. I don't know.
Yeah,
so that's another interesting question. Actually, this conversation is, yeah, it's yes.
No, I mean, you know, I thought a bit about this P equal W long ago, before the great recent events, you know, changed the field. But nevertheless, there is a way to think about P equal W in. I mean, the question is, your question is, what should we take instead of the character varieties? Yeah, and you can think like this: you have a complex symplectic, say, manifold for simplicity, not stacks, nothing sophisticated, like sort of a moduli of Higgs bundles. And then this character variety is obtained by the complex structure rotation. Yeah, like you move along the twistor CP1. Yeah. And apply the Riemann-Hilbert correspondence. Like first you have Higgs bundles, then you deform it to this lambda connections of delineant, then you apply Riemann-Hilbert, and so that's what you get. Now, you can do the following. You can look for your moduli of Higgs bundles, say, sitting at 0 and infinity in this twistor CP1, and take and try to construct a twistor family of categories. And the proposal, which is related to our project with Maxim on holomorphic Floer theory, is that you should take the Fukaya category. So in the variable point, except of 0, say, and infinity, where you have something which does depend on the complex structure, like moduli of Higgs bundles, you should take the Fukaya category of the same complex symplectic manifold. but with different, of course, symplectic form. And the thing is that the character variety, it's representation of the fundamental group, yeah?
Mm-hmm.
The same as modulo of the group algebra. And there are some simple results in symplectic topology, maybe not simple, like it's really generation criterion of Abu-Zaid, which said that the rapt Fukaya category of the cotangent bundle is generated by the fiber, one cotangent fiber. Like, for example, for the cylinder cotangent bundle to the circle, you take just one cotangent line. And so it generates the Fukaya category. And endomorphism of this cotangent bundle is a DG algebra of pointed loops on the base. So if your base is a curve, Riemann surface, like KP1 space, then it's exactly group algebra of the fundamental group. So then you can recover your character varieties from endomorphismal generator in certain Fukaya category. Then if you do not know what happened, what should replace the character variety, you should look for Fukaya. I mean,
the issue is that you see these moduli spaces or stacks of Higgs bundles with these two twisted endomorphisms are not holomorphic symplectic. They are -1 shifted symplectic. They are -1 shifted symplectic in the right
direction. But that's what I mean, that our picture with Maxim, it's sort of very, in a sense, naive, but probably there is a shifted symplectic generalization.
Well, they have a -1 shifted symplectic structure. I just don't know how to put that in a twistor family.
Okay.
So they behave, in other words, this is the geometry is the same kind of geometry you get for moduli spaces of stable shifts in Calabi-Yau threefolds.
Yeah.
They have a -1. It's not 0 shifted. It's -1 shifted. And I mean, okay, if you think in terms of metric structures, they're not expected to have a hypercalometric. I mean, even if they were smooth and nice, you wouldn't expect them to have a hypercalometric because they're not even.
Yes. But you know, this star story, it's a bit unsatisfactory.
Yeah,
but there should be kind of a more general. I mean, we saw some more general structures when we studied sort of generalization of the moduli spaces.
So you think
monopoles, but some kind of a family of.
So you think it's more like you have a family of -1 derived stacks with -1 shifted symplectic structures.
Well, maybe even not necessarily -1, but in this particular case, yes.
Well, in this particular case, -1.
Yes.
Maybe. I mean, that's an interesting question. I never thought about it.
So there should be a deformation, you know, like this. I don't know. I hear it first time from you, but there might be some deformation of this moduli space of Higgs bundles with two Higgs fields, which is analogous. Yeah.
You should try to convert it into some moduli space of Lagrangian objects, but I don't.
Yeah.
This is what happens when this is one way to think about what happens to character varieties, right? Because
it's really interesting. Yeah. Maybe we should discuss it kind of separately. Ask people any other questions because it becomes.
I have been waiting for.
Okay, Zongzhu, please. Yeah.
First, outsider, could you explain what the OS is?
It stands for Oblomkov and Shende, who formulated this conjecture.
Oh, I see. That's what the OS. I see you formulate. Okay, good.
Yeah.
So, second question was about you mentioned about a safe framed structure. Let me see which
Yeah.
slide. I forgot.
So that's
So
a
could you
condition.
explain where the C framing from the diagram?
Okay, I don't know. This could be an unfortunate terminology. Yes. So I'll show you what I mean by that. Sure. I'll show you what I mean by that. So the C-frame so-called C-frame condition, it's right here. So these are stable pairs. So a stable pair is just a section from it's a pure dimension one sheaf with a section satisfying.
Yeah, F has to be torsion free, and
F is pure dimension one. It's pure of dimension one. So it's a torsion sheaf. It has a one-dimensional support, and it doesn't admit any subsheaves supported in 0 dimensions. It doesn't have so it doesn't have like if you think in terms of structure sheaves of schemes, it doesn't have embedded points or things like this. Yeah. So it's a nice.
When you said that the framing, C frame.
Yeah, C frame means that I wanted to have a specific form. This is the condition here. This exact sequence that's written in the lower part of this.
Lower part is
yeah.
one-dimensional.
So I wanted. So I fix the curve. So it's the fixed reduced irreducible. In this particular case, even plane curve. So it's fixed. So I want this F to be an extension of some torsion-free sheaf on C, extended by 0, by any kind of sheaf supported on the exceptional curve. So I'm restricting myself to a very specific kind of object. It's a submoduli. It's a moduli subspace. So yeah, defined for these conditions. Yeah.
I see. So you want the quotient to be torsion free on C. Of course, everything is living on sigma. C is contained inside of sigma. Right?
No. Everything living in Y. So the picture is this. The picture is right here. This will help us to get some more idea what's here. You see, you think of this as an ambient threefold. C is C plus. I dropped the pluses because anyway, it was convenient.
I see the C plus.
Yeah, so C plus is
with only one single point.
Yeah, and sigma plus is another curve. This sigma plus is just a smooth rational curve, so it's a projective line embedded in my threefold, and they collide at a single point, and so I want my sheaf to have to be made of a sheaf on C plus and extended by a sheaf on sigma plus. But the support conditions are important, so they so you have to import some kind of support condition. Because a priori
now I got the sense of what
a priori that sheaf F could be supported on any curve that passes somewhere here, does all sorts of things here. So I want to rule those out. So yeah, I import some support conditions.
And my third question is that you have this flag Hilbert schemes, which is actually 2 steps of flags. In this definition.
Yeah, here this is the flag Hilbert scheme. Yes.
So what have I mean here from this one you could also embed inside of the Hilbert scheme with K plus H, right? So just forget the I just go directly with the I prime in this.
Oh yeah, you can you can map this you can map this to the Hilbert scheme of defined by sure. You have a forgetful map.
So in this case, does it as L and the K varies, does it define some kind of multiplication, in particular on the invariant side? Or
you mean you're asking me if there is a convolution product? No, I don't know how. I spent some time doing this.
So for example, if I have this Hilbert KL, and then with
you're thinking of some picture like in Nakajima's construction of Heisenberg algebras, like where.
Well, I'm thinking of a flag. Just take it here. I could take the top section, and also take the bottom parts, and the extension that get me something much longer, which is the sum of the K and the L. I guess you probably didn't think of this.
I mean, one thing I
there
thought
are
about,
maps.
one thing I thought about is that you can project on I prime and on I. So you have so if you want, if you think of this as some kind of correspondence, let's call it variety. It's just whatever scheme variety. So you can try to construct some Hecke transforms, or say you can try to construct some convolution product. It technically doesn't work because of this.
And from this one can set to the Hilbert's K plus L, but forgetting the middle I.
Yeah, you have a map to Hilbert K and have a map to Hilbert K plus L. That's correct. Because L is the length of the yeah. You have two maps, so you could envision doing some convolution for Borel-Moore homology or whatever. It just you play back
That's
forward.
That's what I was thinking.
Yeah,
whether
you could envision that
Borel-Moore homology or even over finite fields, you count the number of points.
I never thought about it over finite fields. Over finite fields, it might work if you act on constructible functions, because then it's all there. It might work. What I try to do is construct something on the Borel-Moore homology, and that didn't work. Technically, it doesn't work because you can't define a virtual pullback, and the thing that gets in the way is this condition written in blue here, the very last line of the. It's this condition written in blue at the bottom of the slide. It's because it's a scheme theoretic. It's a scheme theoretic condition.
Oh, I see. Okay, here you
that
have
is,
want the support to be.
Yeah, it's a scheme theoretic condition that messes up all your, if you want, all your cotangent complexes, and you get amplitude. The amplitude is too long. It's too big. Well, I mean, the cotangent complex doesn't have amplitude. It's not. Yeah. Anyway. So yeah, technically it doesn't work.
Actually, this will get to my last question about how the singularity. Here the Tn, I guess that's probably you fix to
you mean Tn?
Kind of reflecting the An singularity. Am I right?
Tn. Tn. No. So first of all, let's clarify. So here on this picture, on this side. My threefold is smooth. This is a resolution. This is a resolution of a threefold is smooth. Everything S plus is smooth. Sigma is smooth, and C plus is singular. Tn is because by the geometry, what the geometry gives you is a canonical sequence of scheme theoretic thickenings of sigma. So that's built in. That's built into your geometry. You know, it's. If you write, which we did, we wrote explicit formula equations for everything, and yes, you get a sequence of thickenings, and then you take sigma plus and you intersect it scheme theoretically with S plus, and you get some kind of zero-dimensional
stuff. The An singularity you mentioned that earlier.
It's inside. Yeah, the way you have to think about this, it's a very strange thing, but after so much working on this. The An singularity occurs on the other side. So on my other side,
on the negative side.
On the negative side, S minus has an An singular point right here at this corner, at P minus. At P minus, I keep forgetting that. Oh, you probably can't see the.
Yeah, I see it. I see it.
Yeah. So that's where the singularity is. But this Tn, this scheme theoretic condition that I'm using on this side. Is in some secret way related to the presence of the singular point here. Yes. So there is some. It's a. That
was also the length of the filtration you mentioned. That's
it's the length. It's the length of the filtration. Yes, it's the length of. That's what I'm saying. It's all determined by the geometry. So that Tn has nothing to do with C plus. It's determined by the geometry. It's given to you once. Yeah.
So how does the An singularity on the negative side play the role?
Well, it's singular because that's the whole point of the setup. Because S minus is singular at P minus, this curve is not a plane curve. It's a singular space curve, because it's not. You can't write it as a vanishing of a single polynomial equation in a smooth surface. It's inside the surface, but the surface itself is singular. which means you can't write it as a single zero locus of a single polynomial equation in a smooth surface.
That's why you look at the special case of a local.
And you can write it,
intersection.
but you can write it, at least in the nicest examples we have, we can write it as, I'm losing track of my slides. Where is this here? You can write it as the zero locus of two polynomial equations in the ambient
So this is a
region.
complete intersection.
Yeah, in this particular case, it's complete intersection, but because I picked up my examples to work this way, in generic situations, it's not even complete intersection. In generic situations, it's got just a very ugly singular curve, singular scheme. Yeah, and as I said, if I start changing these equations even a little bit, I can't even find a set of generators of the defining ideal. Even that is a hard problem to find it, to find a set of generators. So
what happens if there is no singularity? All the points P plus P minus are smooth points.
Yeah,
Those
are the degenerate examples. In that case, what you get is something very similar. It's basically very similar to the conical flop used by Davesh Maulik. It's a relation between two plane curves. And it's very important because that was very important in his proof of the Oblomov-Shenday conjecture. But this is not what we wanted to do. For us, that's not. We want to step up to. So,
okay, thank you very much. I really appreciate your patience explaining to my questions.
More questions? Well, if there are no more questions, and thank you very much for very interesting and inspirational talk.
Thank you, Jan.
And then this is it for today. Maybe I will ask you.
Yeah, maybe we can meet some other time and then discuss some more. Yeah.